our project, as we portrayed last time, is still simulation-based inference to simulate or for parameter estimation for stochastic gravitational wave background, likelihood free to be specific. Yeah, we have Lexi and Daniel. Lexi and Jijong is over there, and Abby is joining us over Zoom. You're advised by group kids. I'll win. And it's just introduction. And this is our basic setup. So to begin, we have simulated data from simulator that we were given, and from this we wish to essentially build a machine learning model for dimensionality reduction, so we can recover most of the original data in the end after training a model. So we hope to, using that data, train an SBI model. So I guess I should go a little bit into what SBI is for an introduction. We'll go much further in later on, but SBI is a form of parameter estimate, or is a method that we can use for parameter estimation without knowing the likelihoods. So specifically, we want to recover the posteriors of parameters, which are the spectral index in alpha. So we hope to train an SPI model to perform this parameter estimation. And then later on, we want to recover our parameters from specifically the isotropic case before eventually we need to extend it to directional switch or the anisotropic case of the gravitational wave background. Yeah, so currently our understanding is that we can model our energy density as power law of power of the frequency. So for the isotropic case, we don't necessarily need to use SBI. We just can use traditional Bayesian analysis methods to model and to perform the parameter estimation, because we have a specified likelihood function. However, our problem is that in the anisotropic case, there's no closed form. It rather specifies as it's rather a multivariate chi-squared likelihood function. So as a result, there's not a clean closed form. So as a result, we don't have clear likelihood. So generally, we need SBI. So over this past semester, we've done a little bit of tuning and testing of our models. So specifically, we realized that our variational autoencoder model, which was our model for dimensionality reduction, was overfitting. So during our pre-processing and before, specifically due to the splitting of the data. So we slightly optimized it, and we'll go a little bit further into that in methodologies. We tuned our VAE models so that it was better able to recover the data. And we were able to use a Swift package, which a Swift package is just for SBI to perform our parameter estimation of log ratios. So in this case, our SBI method is a truncated marginal neural ratio estimation. Each of those words have we'll find out in a little bit.
You can also click it.
I'm responsible to explain the part 2, the background, and I will introduce the background, particularly specifying in SBI simulation-based inference. And our research is trying to do some parameter estimation from the gravitational wave background. So, and our goal is to infer the parameter with observations. And for the gravitational wave background analysis, Bayesian method face 2 challenges. The first one is like Daniel mentioned, we have no closed form for the multivariable chi-squared likelihood, but as we know, we need to confirm the likelihood when we use a Bayesian method. And the second one is that the gravitational detectors often give us high dimensional frequency data. So it's too expensive to compute the posterior directly. So this is where the SBI gave us a likelihood-free solution. So it's like the core idea is that we replace the mathematical derivation with the simulate data. And we try to learn the relationship between the data and the parameters directly. Actually, generating data by using the simulator can also be thought of via doing the sampling of the exact likelihood. So how does SBI work? And for the first step, generate training data, we use physical models to generate data. And the parameters are sampled from the priority distribution, which covers a range of the parameters theoretically. And for the second step, we try to learn the evidence ratio. So we train the neural network to learn the evidence ratio. It's also like we are doing a binary classification problem. We distinguish the data parameter highly correlated samples from these data parameter independent samples. And for the third step, we use the learned ratio model to learn the posterior with the observations. And here we can see the differences of MLE, Bayesian method, and SBI. And I want to make it clear here is that we can also see the forms of the evidence ratio. So it equals to the left part, the likelihood ratio, and it also equals to the right part, the joint distribution over marginal distribution. So we can do the computation for the right part from our simulated data. And in other words, it also means we are learning the left part, the likelihood ratio.
Okay, hi everybody. Can you hear me?
Okay.
Hello. Hi, can you hear me?
Yes.
Okay, awesome. Hi everyone. I'm just gonna quickly go through our methodology, which is pretty much the same as our update event last semester with a few tweaks that I'll just make sure to address. So then we can get into the interesting new stuff that Lexi's going to talk about, which is actually applying the simulation-based inference. So you can go to the next slide. Yeah. Again, just to recap, our first goal for this project was to reduce the dimensionality of our data. Just because the original data set is 4,096 dimensions is too big to just throw into the log ratio estimator. So this is like the first machine learning task we had, which you can just go to the next slide. And I'm going to talk a little bit about our data set itself. So as Daniel mentioned, we generated data using a simulator, which again, assuming the data follows this power law assumption with two parameters, the spectral index alpha and the amplitude omega. So we sampled from the prior distributions for both of these parameters to generate a large sample of data points with which we saved the ground truth value as well as a noisy version of the signal where we just inject Gaussian noise where basically the variance changes based on the frequency. So on the right here are just three example generated data points. The clean signal with the noise overlaying in black there, as you can see, the noise varies a lot with the frequency. Ultimately ends up being a 4,096 dimensional data set. So to shrink this down, you can go to the next slide. We use an autoencoder structure, which works well for this kind of task. Specifically, we used a variational autoencoder, which varies from a traditional autoencoder in that instead of learning this latent space vector that's deterministic based on one particular input, it learns a distribution. So in this latent distribution space is a normal distribution with a mean and standard deviation vectors. So then when we do the decoding, we actually sample from this latent distribution each time. Again, the goal for this task is to train a model that is able to, given the noisy signal, learn the clean signal well enough that we can just take this first part, so the encoder, that basically will just be shrinking our data down from 4096 dimensions to this smaller sampled latent vector. So next slide. This is the architecture that the team worked on. So some changes from last semester. First, they added 3 more layers in both the encoder and the decoder, so it's a deeper structure. Secondly, the team increased the latent space from 16 dimensions to 32. So it can hold a little bit more information, but it's not so large that simulation-based inference can't handle. Also, the dropout originally was applied to all of the layers, but they changed it so that the dropout is now only in the initial 3 layers of the encoder and the final 3 layers, so the shallower layers of the model, just because these are the layers with more dimensions in order to help prevent overfitting. And when dropout is applied to the deeper layers, because they're smaller dimensions, it can result in a loss of information. So next slide, the performance estimation is also pretty much the same. We stuck with this custom loss function that we developed where it's basically just the mean squared error, but we weight it by the variance because that varies based on the frequency, as well as this regularization term called KL divergence. And this is particularly for variational autoencoders. KL divergence helps to ensure that the latent distribution space doesn't stray too far from your sample or your standard reference prior, which in our case is a standard normal. One change, however, is this new hyperparameter patience of 5 basically just means that over the first 5 epochs, we slowly introduce this KL divergence term. And then after the first 5, it's fully added into our total loss. This just helps prevent runaway training and validation loss. So next slide. This was after model training, just an example of the variational autoencoder performance. And basically it works well enough to move on to the next step, which I'm going to hand it over to Lexi to talk about.
Yes. So actually, so the variational autoencoder, this is on the left, like the recovered signal after injecting the noise and then removing it. So it works pretty well. And then the training loss, the test loss and the validation loss are right on top of each other in this image. There is a caveat to this, which I'll try to get to in a second. So now that we have successfully accomplished goal 1, we would like to train our SBI model to perform likelihood-free inference. So just a recap of what we're putting into the log ratio estimator is we're putting the part in the red box, and we're feeding that into the SBI network, the package Swift that handles this, and it just trains this model using these training specifications. So we give it a patience of 3 for early stopping for validation loss, and then our loss function is binary cross entropy, which is pretty standard because the probability of drawing a sample marginally or drawing it jointly is equal. And so we would like to figure out which one so that we can figure out the likelihood to evidence ratio. So this is an example of our SBI round function. So step 1, we simulate our samples. That's the simulation part of SBI. And step 2, we pre-process our data, which is shown in the box. Step 3, we train just the encoder part on our log ratios. We marginalize over the 2D posterior, the 2D parameter space. So this is the marginal neural ratio estimation part. And then we perform inference with clean priors. And then after that, we collect new bounds in step 5, which is the truncation part. And we put those new bounds back into the simulator and the new priors, and we rinse and repeat this process. So since we're kind of out of time, so now we've done step 2 and we're just gonna talk about recovering our parameters. So, this is the caveat I was talking about. So I realized within the last like 12 hours that the priors for the parameter estimation and the priors for what I showed for our VAE are different. So for our parameter estimation, we're actually using a uniform distribution instead of a log uniform distribution. And this is an inconsistency that needs to be addressed, because if we're saying our original model works well, then we shouldn't change the priors before performing parameter estimation. But ignoring that, we can see that omega and alpha have their 1D posteriors on the left and then the 2D posterior on the right. And if you can see the shaded regions in the 1D posteriors, it corresponds to the contours of 99.7, 95.5, and 68.3 credible intervals. Yeah, I'll skip the slide. So truncation and bounds, this is the T part that we want to talk about. So the ground truth is up at the top, and then the black dashed lines on each plot represent the ground truth. So our round 1 is shown in fuchsia, the round 2 is shown in cyan, and the round 3 is shown in gold. And you can tell that it recovers omega quite a lot better than alpha, and you can see how the bounds change over the rounds. Just real quickly, comparing this to traditional Bayesian methods, we can see that there's about 3 orders of magnitude between our standard deviations for omega and for alpha. Our Markov chain Monte Carlo is like perfect basically, which is great. And yeah, you can maybe see the red dashed line is right over the gray. Yeah, sorry, out of time. So immediately we need to look into our prior distribution inconsistencies. Originally we set out to extend this to the anisotropic search, so we'll have to build a different simulator. And then there's a few other things there, but since I'm already over time, I'll stop. Oh, and we also want to thank Hao Wen for all of his work and Alex G for some conversations that were helpful as well, and Book.